Okay, so the data structure that was assigned to us for DS2 project was a range tree. So basically, a range tree is just a simple binary tree, right? But with some different properties and a bit of different structure. And the specific quality of range tree is that it can store the n dimensions data in it, and we can and it can efficiently let the user search for the range queries for different ranges in different dimensions, and we'll see that in the coming slides that how we can implement that, and we'll look that in our application too. So that's the idea of the range tree. Now, so basically, range tree is just a binary tree. So what's so special about it? So for looking for the discussion of the range tree, and it's been going through its papers and all of that, we found that there were two major properties of range tree. One, that each value in a whole range tree, every value in a whole range tree is stored in its leaves. Like all the, if you want to go through all the values of a range tree, you can just go through its leaves and you will get all the values stored in that range tree. And what about the other nodes? So other nodes, other than leaf nodes, each node contains the value which is highest in its left subtree. So that this helps in range querying a range tree within the specific range, and we'll see how it helps. But yeah, these are the 2 points that we have to keep in mind when building the range tree and writing its add function and all of that stuff. So yeah, these are the two major properties of range tree. So a range tree can be basically of n dimensions. So this is basically just a one dimension range tree which is storing just simple points. And if you want to see all the data stored in it, you can go through all of its leaves, and each node contains the highest value in its left subtree, as you can see here also. So this one dimension range tree, for higher dimensions, you can see that each in higher dimension each node contain a pointer to another range tree. So basically we will talk about it what that other range tree contains. This node has its own subtree here which contains all of these values. All of these values are basically sorted on x-axis. The pointer it contains to a range tree, it also contains all of these same values, but arranged but sorted on y-axis. So basically this is a two-dimensional range tree where here the 2D range tree is sorted on x-axis, and it has a pointer to a 1D range tree which is sorted on y-axis. So that's the idea of basically a 1D and a 2D range tree. Now we look at how we can search in the range tree. So basically, if you like, you have these x and y axis coordinates, and you have like millions and billions of points in it, and you want to find the points that comes within this square area. So as you can see here, it is just 3 points, but it can also be it will depend on the data set that we be using. So basically, if we want to find the points between the this x range and this y range, so this can be easily done, this can be efficiently done by the range tree. So we look at how we can search in this. So basically what range tree does is it just like it will, if it's a 2D range tree, it will start from its root node and find the point which contains which lies within the range. Like if you are searching in for the range for the points between 10 and 20, and the first node that we find in a 2D range tree that falls between this range, from that node we'll go on to that the pointer that it is pointing to the 1D range tree, and in that 1D range tree we'll search for all of the nodes that fall within that range in within that given x coordinate range tools, and we will return all those. So this is how range trees basically work, and this is the complexity. As you can see that space complexity is not so good because it is storing multiple times each value in its if it's a 1D range tree, it is at least storing the value twice. If it's a 2D range tree, then it is storing values multiple times, because every node has a pointer to its subtrees. So yeah, space complexity is not so good, but time complexity is much better, which is O log power d n plus k, where n are the total number of nodes and d is the number of dimensions of the range tree that we are working on, and k are the number of results required. Like if we have millions of results for a range query, we can specify k, we want top 10 results or top 100 results, so that will be our case. So this is basically the time complexity of the range tree. So this is the basic idea of our data structure. Now we'll move on to our application as to what we'll do with this data structure. This is just the tasks that we divided at the start and completed on our own, and then collaborated and then completed our application. So yeah, that was it. Thank you.